Welcome to Plutus. So today we are going for the lecture number 5 for coordination compound, and in today's class we'll talk about the isomerism that is seen in coordination compounds. Specifically in today's class we'll only limit ourselves within the structural isomerism, and in the next class we'll go for optical and geometrical isomers. So the isomerism in coordination compound is seen for two types. First is the case of structural isomerism. The isomerism which is characterized by change in the coordination complex. Either something gets added in the coordination complex or something leaves the coordination complex, or there will be change in the attachment of the groups that are present within the coordination complex, leading to the alteration of the formula of the compound. There are total 4 types of structural isomerism in coordination compound. First being your linkage isomerism, then we have ionization, then coordination, and finally solvate isomerism. Now let's deep dive deeper and let's explore each type in detail. First we have is the case of linkage isomerism. As the name suggests, whenever you have a metal complex, if you have a ligand which can have more than one donor site, if the link between the metal and the ligand changes, that is called as your linkage isomerism. Now if we clearly see, we know such kinds of ligand that can change their attachment to the metal center, and we know them by the name of what? Ambidentate nucleophile. Ambidentate nucleophile. So that means linkage isomerism is a characteristics property of the ambidentate nucleophiles, where the link between the metal and the complex changes like this: Nc whole 6 minus. In the previous complex, the carbon is bound to the metal center cobalt. In the second complex, it is the nitrogen that is bound to the metal center cobalt. Next is the case of ionization isomerism. Ionization isomerism refers to something which can get ionized. In the coordination complex, we know in the coordination sphere nothing ionizes because they are predominantly bound by coordinate bonds. So which can ionize? Our counter ions. So ionization isomerism is characterized by counter ion which have much more potency, or that have more better ability to bind to the metal center, forming a better coordinate bond than being a counter ion. So what it does is, your counter ion invades the coordination sphere and then replaces a ligand which can then become your new counter ion. Such kinds of isomerism is termed as your ionization isomerism. And remember, in no type of isomerism you will ever see change in coordination number. The coordination number of the complex always remains the same. Only the attachment or the groups within the coordination sphere are allowed to change. Example for ionization isomerism: having uh, manganese H2O whole 4 Br Cl minus Cl whole 2, and you have Br as the coordinating ligand here. Wait, Cl2, it should be iron. That's Fe, that's Cl2, and that's Br. So here Br can act as a better ligand, so it will move inside the coordination sphere, removing one Cl, which can then later become the counter ion. The next type of isomerism we have is known as coordination isomerism. As the name suggests, this time we'll be dealing within the coordination sphere. So in this cases, you require two separate coordination sphere which are stabilizing one another. For example, chromium H2O whole 6, and then we have cobalt NH3. Cn whole 6. Here, if you try to move fin, this has a negative coordination sphere while this has a positive charge. So in this case, another coordination sphere is acting as a counter ion for the another coordination sphere. In this, here, chromium can form a better bond with cyanide and cobalt can form a better bond with water. So here, their ligands change their places, leading to the either position of the ligands or inversion of the charge present on the coordination sphere. Now this will turn to 3 minus and this will turn to cobalt H2O whole 6. So when you see the interchange of ligands or metal center within multiple coordination sphere, that type of isomerism is called as your coordination isomerism. And then we have the last type known as the solvate isomerism that just looks for whether the solvent in which the complex is present, whether the solvent is acting as a ligand or just it is existing pure as ligand, taking no part in the coordination sphere. Especially when solvent is water, then solvate isomerism gets a new name known as hydrate isomerism. Hydrate isomerism. Example for the case of Cu SO4, sorry, copper H2O whole 6, and this is SO4 here. Now here the water is acting as a ligand. In another example, you can have CuSO4, which is copper sulfate with 6H2O. Here, water in case of the first complex is acting as a ligand, but in the second case, it is acting as water of crystallization. So, isomerisms in which the solvent act as a ligand and can also act as water of crystallization or another stabilizing unit that can stabilize the complexes. Such kinds of isomerism are known as solvate isomerism, and specifically for water they are known as hydrate isomerism. So I hope this would have cleared all your doubt regarding the structural isomerism. In next class, we'll dive deeper and talk about our optical isomers in terms of it should not be actually be optical isomer, but they should be actually stereoisomers. Okay, please correct it. They should be stereoisomers. And we'll talk about them in the next class. Thank you for joining us. If you still have any doubt, please add it to the comment section and we'll get back to you. That's all for today.